So hi guys, today we have another problem, that is path with minimum effort, and the problem states that you are given a matrix, this matrix, and these values are represented by the heights of the mountain, and we have to start our journey from here and we have to reach here. And there could be multiple paths like this or this, and we have to tell the minimum effort path that we are considering here. And how can we calculate the effort? That is, we have to consider all the adjacent values. So basically, we have to calculate the absolute value of two nodes. That is 1, here is 0, and 3. And if you consider this path, then it will be, there is 2, 2, 2, 2. And then we have to consider all the values for each path, and we can get the maximum values. Like if we consider this part, the maximum value is 3, and if we consider this part, the maximum value is 2. Then we have to return the minimum of them. So that is the problem that we have to solve. So let us think about the approach, what can be. Now one thing is sure, that we have to reach from this node to this node. Now we have to calculate the shortest path, right? And when we are talking about the shortest path, then obviously there are two algorithms, that is Dijkstra and the Flight. And since we only need for one ending point, so we don't need to bother about the Flight. Dijkstra will be enough. And also there is not as such of negative cycles, because they are telling that the constant, the value will be 0 to 10 to the power 6. So we can use Dijkstra here. So let us try to modify the Dijkstra approach and try to solve this question. So let us first recall the steps of Dijkstra algorithm. Then we will go to the main approach. First of all, we have to modify the Dijkstra algorithms a little bit. Look, first of all, we have to declare the distance array, and here we cannot take only size of n, because the given matrix that is n cross m. So we need to make a matrix that will be n cross m. Okay, so then we have to take the priority queue, and that is same for here also. And then we have to initialize the starting node with 0, and also here it will be same. And just we have to keep two variables, that is for I position and the j position. Initially both will be 0 and 0. So this is the modification that we need. And in the first next step, then the modification will be get the minimum weighted node, that is obvious, that will be same here. And the all nodes that is adjacent, we have to visit all the adjacent nodes, this will be also same. And we have to check this condition, the main condition, when we are updating the distance matrix. So we have to change this condition here. So the condition is basically, they states that if I want to get the efficient path, means efficient effort, that how can I get that? Basically, we need to calculate all the adjacent node, that is absolute value of the adjacent node, and that should be maximum, and that should be also less than the distance of the current node. So that is the main point of this algorithm, and the main condition is to satisfy this situation. So let us try to write the condition, that is basically uh, max of the ABS of, let us say the name, suppose this is the height of the matrix that is given to us, height of previous I and previous j, that will be the previous value of the height. And we have to subtract it using the current height value, that is height of current I and current j. And how can I get this current I and current j? Basically, these will be our adjacent nodes. The current nodes means we are getting all the adjacent node, right, for every situation. So this will depict us the adjacent node of the current node. So we have to subtract it to get the ABS value of the current uh, effort, and we have to keep it max with whom, that is the previous distance. If this condition satisfies, and also we have to check this value should be less than the distance matrix, and then we can update the distance matrix as well. So what will be the distance matrix? That will be here, uh, current of I and current of j. So we have to modify the distance matrix because we cannot take a single array. We have to take 2D array to store the distances. And here, so that is our approach. And obviously, then we have to store all the values into queue, and that's why we can move for the next iteration. And so yeah, this is the approach. Let us have a dry run, then the concept will be clear. So let us have the dry run, and then it will be clear to you. So this is the condition that we need to satisfy. So basically what it tells that you have to calculate the absolute value of the previous weight and the current weight and the previous distance. We have to get the maximum value of those. And if the maximum value is less than the current position distance value, that is this vector, so we can then update the distance value, right? So let us start the iteration. We will start from here. So for starting position, already we do not need any weight. So the weight is 0. And we have to put the element, the position of the element and the weight here. So then let us run a while loop, and until and unless the queue is empty, we will continue. So let us pop this right now and get the adjacent nodes. And what are the adjacent nodes? That is 2 and 3. So the absolute value of this thing, like the previous value is 1 and the current nodes are 2 and 3. So we have to calculate the ad, absolute values, that is 2 minus 1 and 3 minus 1, that is 1 and that is 2. And we have to check either the previous weight, that is 0, and the current weights, that is 1 and 2. So for this position, the current weight is 1 and the previous weight is 0. We need to have the max value. So the max value is 1, and it is smaller than the current position element. Obviously, yes, because initially it is infinite. So we can update the 1 here, and the same will be here also. We will update it by using 2. So now we have to push these values also, the positions. So the position is 0, 1, and the weight, that is 1, and 1, 0, and the weight is 2. Great. Now, what is the minimum weight? That is this one. So we need to push, so we need to pop this one. Let us erase this. Okay. So now we have this node. So we can consider the adjacent nodes of this. So the previous weight, but that is 1. And okay, let us make this thing clear. Previous weight, that is 1, and the current weight, that is for the adjacent nodes, that will be written here. Okay, so the previous weight is 1, and the adjacent node, that is 2. So 2 minus 2, that is basically 0, and here 2 minus 8, that is 6, and 2 minus 1, that is basically 1. So let us compare for the previous node, so previous weight and the current weight. So which one is greater? That is for here, that is 1, obviously. So is the 1 lesser than the current value? Obviously, yes. So we can put 1 here. And for this node, basically for this node, the weight is 6, and we can put here 6 because the maximum value of 1 and 6 is 6, and 6 is lesser than this value. So we can put 6 here, and as well as we have to check for this position also. So the weight is 1 and 1. So the maximum weight is 1. 1 is not lesser than 0, so we cannot update it. So which cells are updated? That is this one and this one. So we have to put the positions also in the priority queue. So what is the position? That is 0 and 2, and the weight is 1, and for here it is 1 and 1, and what is the weight? That is 6. Okay, so now let us consider the minimum one. So let us remove this one, and obviously we have to erase this at first. So this is the current position, and the previous weight is 1. And what is the adjacent nodes? That is this one and this one. So what is the current weight? That is 2 minus 2, that is 0, and here also 0. So you have to consider the max value of both these two. For these two, the maximum weight is 1, and we cannot consider 1 because already there is 1 here. And for here, the maximum weight is also 1, so we can consider it 1. So this cell is updated, right? So we have to push into the queue, that is 1 and 2. And what is the weight? That is 1. Fine. And now let us erase the current values. Okay. So what is the minimum value right now? That is this one, right? So now we are at this element, and what is the weight? The previous weight, that is 2, and we have to check for the adjacent nodes, that is this one, and this one. So for this, the ABS value, that is 2. For this, the ABS value is 5, and this, the ABS value, that is 2. Now we have to compare the max values. So what is the max value in both two? That is 2, and 2 is greater than 0, so we will not update this one. And for 2 and 5, the greater value is 5, and for this position, this is already 6. So 6 is greater than 5, so obviously we can update here. So what is the eraser? Okay, so let us update here with 5. And what is for this position? Basically, that is 2 and 2. The max value of this one is 2, and the current position, that is initiated by infinity. So you can update using 2. Great. So this cell and this cell are updated. Now we have to push this into our queue, right? So what is the position? That is 1 and 1, and the weight, that is 5. Great. So now we have to push this one also. That is 2 and 0. And what is the weight? That is 2. So now what is the minimum one? That is this one. So we can pop this one. Let us, okay, fine. So we popped this one, right? So the position, that is 1 and 2, this one. Now we are at this 2. So what is the adjacent nodes? That is 2, 8, and 5. Let us write down here. What is the previous weight? That is 2. And what is the adjacent to it? Basically, if we calculate the ABS value, that is 0 here, and that is 6, and that is 3. So what is the maximum value of 2? That is 2, but we already have 1, so we cannot update that. So for this, the maximum value is 6, but we have 5 already here, so we cannot update. And here, that is 2 and 3. What is the maximum value? That is 3. Yes, we can update here. So this cell is updated. Now we have to push the position into the queue. And what is the value? That is 2 and 2, right? So 2 and 2. That is 3. Now what is the minimum? That is this one. So we can pop this. And great. So current node is this one. Now we are at this one. And what is the previous weight? That is 2. What are the uh, adjacent nodes? That is 3 and 3. So we can easily calculate the ABS value. That is 2, and here that is 2 also. So what is the maximum value? That is 2, and already there is 2, so we cannot update that. And for this 2 and this 2, yes, the 2 is the maximum value is the 2, so we can update 2 here. So we have to push this one into our queue. So what is the position? That is 2 and 1. And what is the weight? That is 2. Okay. So let us move to the next iteration, and let us check for the minimum one. That is this one. So pop this. So now what is the mm, previous weight? That is 2. What is the adjacent nodes for this one? That is 3 and 5. For the previous value will be 2. And for here 5, sorry, and 8 and 3, that is 5. And here that is true. Okay. So what is the maximum value? That is 2. That is we already have here. And for this one, that the maximum value is 5. And for which node it is? It is just that one. Already there is 5 here, so we do not need to bother anything. And here the maximum value is 2. And now you can carefully see that there is already 3 here, so you can update with 2 because 2 is lesser than 3. And that is our answer. So if we start from the this node and restart this node, so the minimum effort that will be 2. So yeah, you can check for this one also, but there will be no benefit for that. The answer is 2. So this is how you can make the approach for this question. Just you have to slightly modify the Dijkstra algorithm, and then you can easily get 10. So let us move to the coding part. So I have already written all the initialization part. Basically, this is the distance vector, and this is the priority queue, and we are initialized the starting position with 0, and we have pushed the value, that is weight of 0, and the current position, that is initialization position, basically 0 and 0. And this is the coordination vector, means we have to go to the right, left, and bottom up, right? So this will depict the direction. So let us try to write the code. So basically, we have to, first of all, we have to get the previous distance, that is into this will be PQ of top of first, because this is dedicated for the weight, and this is for the IX position, basically the I position, and that is PQ dot top dot second dot first, and this is for IY PQ dot top dot second, right? So now we have the previous node position and the distance also. So now we have to pop the node pq dot pop, and now we can have all the adjacent nodes, that is int I to 0, I less than 4, I plus plus. Because we have only four directions, and let us have the all the adjacent nodes, that is in car x, that will be ix plus the new position, that is this, and car y, that will be y plus y, that will be I. Basically, now we have added all the values to the previous node position to get the new direction, and we have to also check if these directions are valid or not, because it will go outside of the matrix and cause out of bound exception. So we have to check for that. That is car x greater than equal to 0 and car x that is less than rows, and again car y that will be this, and car y that will be lesser than what, columns. Okay, and we have the main condition, that is we have to get the ABS value of two adjacent nodes, basically the current nodes and the previous node, that is ABS of heights the previous node, that is IH IY minus heights car X car Y, and we have to compare it for with the another value, that is the previous weight, and that is distance that we have stored here, and we have to take the max value of this, right? Max. And let us close the bracket, and if this value is lesser than the current distance, then we have to update, and that is car X car Y. So now we can update the value, and we are copying this value because we will need this one, and the distance car X car Y that will be updated by this value, and also we have to push this current position and the weight into our priority queue, that is that push. We have to insert the weight at first. The weight is distance car X car Y, and the position, that is new position, that is car X car Y. Okay, so I think everything is clear, and let us try to run the code. Okay, it is doing some error. N was not declared. N, okay, sorry. I have put N here. Okay, so the answer is matching. So let us try to submit the code. Great. So it is working, and we have got the gigabit right now. So this is the approach. And let us talk about the time complexity. So what can be the time complexity? It will be simply n into m, and also we are putting this value into the priority queue, and priority queue takes log n to for insertion, and the space complexity, obviously we are using the priority queue, and the maximum space it will take near about n plus m, basically the height. So yeah, that is the approach to solve this question. Just you need to modify the Dijkstra algorithm, and you will get the answer. So it is a good application of Dijkstra algorithm, you can say. So thank you.